Welcome to this video in which I'm going to teach you about mathematical induction. We're going to use a process called mathematical induction proof to show that this statement here is true. This means the sum of the numbers 1 plus 2 plus 3 plus 4 up to n is given by this formula. In a previous video we looked at an example of that where n was 100. And we showed that the sum of the first 100 counting numbers was 5050 using this formula, but now we're going to prove it works through this process of mathematical induction. Now it involves 4 steps. Basis, we test the result when n equals 1. That's the starting point. So n is an integer, it's a whole number that goes up in ones starting at 1. We assume that it's true for any value of n, any other number other than 1, 2, 3, 4, anything that's a positive integer. And then the induction is the part where we show that if it's true for n equals this particular number k, then it's also true for the next number, k plus 1. All right, so in other words, if it worked when we used n equals 4, it would work for 5. And if it worked for 5, then because it works for the next number, it would work for 6, and so on. So it's a kind of domino effect. And then the conclusion, which clearly summarizes what processes you've applied to come to that answer. All right, so now I'm going to show you how it would work in this example, okay? And it requires a lot of algebraic manipulation, and you'll see why in a moment. So we're going to do the basis first, and it simply means that we state that when n equals 1, does the statement work? Okay, well, let's see. When n equals 1, okay, it gives us or implies that a half of 1, okay, because it's a half of 1 times 1 plus 1, okay, should equal 1, and it does, okay, because a half of 1 is a half times 2 is 1. So what we're saying here is that the sum of the first 1 number is 1. Well, of course it is, because 1, when you add nothing to it, is still 1. But we've proved that works by putting 1 into this formula and getting 1 out. Okay, seems very obvious, but we have to do it. That's the basis step. Okay, and the basis comes in here like this. Okay. And you'd normally write that down. I've just saved time by pre-writing these statements. Okay, and then we go on to the assumption. Now, the assumption is simply that we basically replace the n with k. So we just say that for n equals k, we're going to assume, okay, that it's true. In other words, that the sum from r equals 1 to k of r is equal to a half of k times k plus 1. So we've literally just replaced the n with a k. Okay? So it's not actually that difficult, you've just got to follow the process, and that is the assumption step, okay, which has to be shown. Now, it does get more complicated now, because what we have to do is do the induction bit, okay, and this is how it works. So the induction is to show that if it's true for n equals k, it's also true for n equals k plus 1. Now what we do here is we say that when n equals k plus 1, okay, we have this situation, okay. We take the sum from n to k as normal and add on to the end of it the extra term, the next term, the k plus 1. So we say that that implies that the sum from r equals 1, okay, up to k of r plus the next term, which is k plus 1, okay, and that equals a half k, yes, times k plus 1 plus k plus 1, okay. So in other words, I'm just adding k plus 1 onto the end of the series from 1 to k to give me the sum with the next term included, okay. Now when you work on that, you get a half k squared. In fact, I'm going to take it out like this. I'm going to write it as a half k squared plus a half k, okay, plus k plus 1. I'll do all the steps, okay. Now I can take out a factor of a half from the whole thing, okay, and that will give me k squared, okay, plus, now this is going to be a half k plus k, which is 1.5 k, but I've taken out the factor of a half, so I need 3k, okay, plus 2 to compensate for this half that I've taken out. If you want to check that, you can just multiply that bracket out and you would get that, okay. Now the quadratic that we've got here in k will factorize, and it gives me a half of k plus 1 times k plus 2. Now what we have to try to do now is manipulate this so it's in this form here. Now that could be written as a half of k plus 1, okay. So in other words, the k plus 1 is like the n in here, and then in the second bracket the k plus 1 is this n, but it's k plus 2, which is k plus 1 in the bracket plus another one, okay. So what I've done is I've made this formula here look like this one, okay, and simply wherever there's an n in here, there's a k plus 1 in here, okay. And what I've done is I've effectively shown that this is the same as the sum from, perhaps I should do that on a line below here, it's the sum from r equals 1 to k plus 1 of r, okay. So that is the process of induction that I've used to create this sum here, this series here, which is the same as this series with this extra term added. Okay, so my conclusion can now come into place. I should say, by the way, at this point, that's the induction that we've just done. So next to that, I need to state that that's the induction. If the statement is true for n equals k, then I have shown that it is true for n equals k plus 1. Okay, that might want to go down here with the result. Okay, and finally you must have a conclusion. Now I haven't got room to squeeze it in underneath there, so I'm going to put it over here, but that should come really right at the end, okay, after you've done everything else. So I'll put that over here and I'll bring this down, because really that belongs at the end there. I'll take this up a little bit. Okay, so it's clear that the conclusion is the last thing that you do, and maybe just put that in its own highlighting. And that's how you set out a proof by mathematical induction. Okay, so a 4-step approach, and these statements are to be learnt and applied almost word for word, really. So what I'm saying in the conclusion is, if the statement is true for n equals k, okay, if it's true for n equals k, it's been shown to be true for n equals k plus 1. That's what we've done here. And as it's also true for n equals 1, it follows that it is true for all values of n that are members of the positive integers. Okay, in other words, 1, 2, 3, 4, 5, and so on. And that's a proof by induction of one of the most simple counting number results. Okay, there are similar results for the squares and the cubes of the natural numbers, but they're much more complicated. Incidentally, induction can be used to prove an existing statement. It can't be used to discover or find a statement. All right, so you can prove an existing known fact using proof by mathematical induction, as we've done here. Okay, so hope you've enjoyed that. Take care.